Hello friends, this is Javed here, and I'm a very amateur rocket scientist, but I want to give the basics of the rocket scientist. Like if a budding rocket scientist wants to know about rockets and what takes them to space and all, this is the basic information that he should have, right? First of all, subscribe down below. Second of all, did you subscribe? Well, if not, just go down, kill the subscribe button, and then come back to the video. Well, let's start rocket science, the basics. The advances will follow in the coming videos. Okay, this is rocket science. Suppose the whole the concept of rocket science depends on the rocket itself. So let's learn something about the rocket, what it is exactly. So this is pretty much how a rocket looks like. It goes up, the gases come out of here. This is the basic image of rocket that we have from science fiction and movies and all. So basically this is a rocket. This is the body of the rocket. This here is a very important part, like one of the most important. That's the nozzle. Okay, this is the body, and this part here up is the payload. That's where your equipment, the electronics, the satellites, whatever you want to take to space is kept in here. Here is the fuel. The fuel is kept in there. Fuel. Okay, so this is pretty much the design of a rocket. Now let's discuss about this nozzle. This is one of the most important parts of the rocket. The nozzle is not just this, not just a bucket kind of thing. Okay, it's something that's more looks like this. It's somewhat like this. Okay, this is somewhat what a large nozzle looks like. This part here is the combustion chamber. This here is the converging part. See, notice it converges here and then it again diverges from here. So this is the diverging part. This nozzle is a CD type. This is the type of nozzle that we use in rockets, CD type nozzle, and the CD, it stands for converging, diverging. This is the basic knowledge that you should have about nozzles. Converging, diverging kind of nozzle. Okay, so this is about the nozzle, the rocket. So now let's discuss something about the fuel. Well, I'm not going to discuss the basics of the fuel because that's not, that's very advanced chemistry and we don't want to do that. But just remember that it has something to burn and some oxidizer, something that has oxygen in it. Or if not, just oxygen, but it has to have some oxygen and something that is going to burn and give you the energy. So the fuel, must have, this is very important, high calorific value, must be non-poisonous. Okay, non-poisonous because of obvious reasons. Okay, we don't want our environment to get damaged because of the fuel. So we want non-poisonous fuel. We want a fuel that's high calorific value, which means a fuel that's efficient. Less fuel, more energy. That's what this means. High calorific value. Calorific value is a scientific term. That means the amount of energy given off when a specific amount of fuel is burned in pure oxygen. That's what calorific value means. Okay, and the fuel should be solid. Can be solid. It can be liquid, or it can be also a mixture of, wait for it, solid and liquid. No gases. Okay, gases are not allowed here. A liquid fuel is more preferred. Why? Because you can control the thrust. You know, if you increase the amount of fuel going into the combustion chamber, you increase the thrust. If you decrease the amount of fuel going in here, going into the combustion chamber, you decrease the thrust. You know, this is here, the combustion chamber. Here is where the burning happens. The fuel comes in, burns off, and then whoosh, everything comes out of here. Now, one thing I forgot to tell you, this follows Newton's third law. Okay, more pressure in here, down here, so more force up there. Force is more here, so that's because you want large amount of force up there. Okay, and another thing, why is it converging? For obvious reasons. You know, equation of continuity. You know, area is inversely proportional to the velocity. So if less area, the gases come out of, you know, gases are already pressurized, and you then decrease the area. So even more velocity of the gases that come out of here with even larger, greater speeds. So more pressure down here, so more pressure up there. That's the whole point. This is similar to your hose pipes in your gardens. Like when you squeeze the end, the water comes out with greater velocity. That's the whole concept of this converging part and the diverging part. That's pretty much a liquid. Why liquid is preferred? Liquid is preferred because you can control the thrust. I told you. Sometimes a sudden push is necessary, and you will see shortly why is that in the coming videos when I discuss satellites and orbits. Okay. Next, we should discuss something related to aerodynamics. In aerodynamics, I will specifically discuss about the stability of the rockets. Okay. Now, suppose you have a rocket like this. Suppose you have a rocket like this. It's going up, and there's wind coming in from here. So the wind comes in here, it deviates the rocket. Okay, the wind from here, it deviates the rocket's trajectory, so it no longer goes up there. Okay, it deviates, it either goes there or there, but not here. That seems very unlikely, you know, but that does happen. You'll see shortly why. It goes there, but not here. So that's the whole point, is making this rocket go there, but that's not done when there's wind. So this is unstable. Rockets are unstable. It destabilizes. So you need to make them stable. Okay. What is a stable system? First of all, a stable system is a system in which, like, if you displace that system a little bit, it comes back to its original state automatically. That's a stable system. What is unstable? Well, the opposite. If it displaces it, it does not come back to its original state, and it goes on and on displacing in that direction. So that's what stable and unstable systems mean. So what is the relation of that in rockets? The rockets are unstable. Okay, they tend to destabilize. So how do you restabilize them? One way is by using this nozzle. You know, using this nozzle. That's something called, well, nozzle isn't called that. That phenomena is called active stabilization. Okay, so active stabilization is something that is involved for stabilizing the rocket using nozzles. How is that? Let's see. Suppose you have a rocket down here and that's going up, but there's a wind from here, so that destabilizes the rocket. The rocket goes there, deviates from its path. Suppose now the rocket is like this. Okay, it's deviated from its path. So now what this nozzle will do is it will turn a little bit, like the nozzles here, it will just, you know, swing like a bell. It will swing like to here, so as to give this part a little push there, so it again stabilizes. You know, it has to keep moving. Like an example, like suppose you're told to balance something like this. Okay, in order to keep balance, you must always keep moving. Okay, I'm not a good balancer, but still, you must keep moving. So if this thing goes like this, you need to push it like this again, to not damage, but to push it again to make it straight, right? So that's what this active stabilization does mean. So there's a whole bunch of electronics involved in this, but I won't discuss about that, okay, in details. That's pretty much it. Another form of stabilization is another means for which you need to know a new concept that's called CM and CP concept. Well, CM, you know, CM is what you expect is center of mass. CP is center of pressure. Okay, what is center of pressure? Center of mass is the point where all the mass acts. You know that. Like, suppose this is a rocket. Come on. This is a rocket. Not getting enough space here. There's a rocket, and you have, you know, this point, the point where all the mass is acting. You know, that's the center of mass. Okay, what is center of pressure? That's the point where the area up and area down are the same. Okay, this is the, you know, here, suppose, is the center of pressure. That's the point where whole of the pressure is assumed to be acting. Okay, so that's the center of pressure. What is the work of this? We'll see shortly. Now, I ran out of space in that paper. Okay, so suppose you have a rocket like this. Okay, and there's a wind and it deviates. Okay, suppose you have a rocket like this. So rockets are always have winds like this. Okay, it's called relative wind. Suppose you're going in a car with, let's say, 10 kilometers an hour, and you place your hand outside. You feel the wind coming towards you at 10 kilometers per hour, provided there's no external wind per se. So this is the relative wind. Okay, so suppose this thing does not affect the rocket much when it's right this upright, but when it deviates because of the wind just a little bit, okay, when it deviates just a little bit, the center of pressure comes into play. Suppose this is the center of pressure. The whole of this wind that's there, and it's as if this whole wind acts at this point. That's the center of pressure, the point where all the external pressure seems to be acting. Which pressure? The wind pressure. Okay, this pressure seems to be acting here at this point. So that's the whole point of center of pressure. So now this will try to pivot this whole rocket about the center of mass. We all know that, and let me write that for you. The rocket pivots about center of mass. So this rocket will pivot about this point. This will turn. So sometimes this destabilizes the rocket. So how do we restabilize it? You know, the stability will depend on the position of the center of mass and the center of pressure. We will see now why. Suppose I have two rockets, identical but different center of masses and center of pressures. Like, suppose this is a rocket, this is again another rocket, and you're going to test these. These are identical. Okay, you're going to test these rockets in wind tunnels. Okay, they spray out air. This is similar to the relative wind that you will encounter in flight. So suppose this rocket has a center of pressure here and center of mass here. This rocket has center of mass here and center of pressure here. Suppose what will happen, let's say this case, we displace this rocket just a little bit. Okay, this moves like this. Now this rocket moves like this, just a little bit. Now the whole pressure will act in here. Like, let's say this is the center of pressure, the center of mass. Like, this thing move like this. So now this air will act on here, pivot this around this point, so it will keep on rotating. There's nothing to restabilize it. This system will be unstable. Okay, what about this thing? Displace it just a little bit. Okay, so this thing goes like this. This thing becomes like this. So now this point is here, this point is here. What will happen? This wind will act here, pivot it about this point, turn it like this. It will again come back to its original position. The same when we displace it just a little bit like this is the rocket, displace it like this. So the center of mass comes here, center of pressure comes here. So this wind acts on this center of pressure to again rotate it like this. So this again comes back to its straight position. That's how you stabilize a rocket, and this is stable. We just learned that the center of mass should be above the center of pressure in order for the rocket to be stable. How to do that? Now one way to do that is, take the rocket and fix a lot of heavy weights over here and to shift the center of mass up, but that's not feasible, okay, because carrying weight to the space is costly. You have to pay per ounce of a lot amount per ounce of weight you carry to space, so that is not economical. So you won't do that. That's not done. So another way is shifting the center of pressure down. How do we do that? Well, in India you have a festival called Diwali, and in Diwali it's a custom for Indians to shoot rockets, and the rockets look something like this. It's very bizarre, but that actually serves the purpose. Now this thing, the rocket is just this. If it's just this without this long thing, I've drawn a nice Diwali rocket for you, by the way. So if this is just this thing without this long stick, this, suppose for example the center of pressure here, mass here, this will destabilize. It will just roam around anywhere and will just not serve the purpose of the firework. So how to stabilize it? We know that we can't add much weight over here. This will be non-efficient, so the other way is increasing the area by adding a lot of a long sort of a stick here. So what this does is this increases the area down here, so the center of pressure comes down, center of mass still remains up because the stick is very light, and so the purpose is served. Now the rocket is stable. That's the whole point, to make it stable. So, but imagine NASA and ISRO scientists doing this. How do we do that? Can we ever imagine a rocket like this? No, that would be just complete hilarious, So one way to do that is putting fins, and that's why the rockets have fins. Like you've seen rockets like this, right, in movies. But that's the whole point, increasing the area down here so the center of pressure comes down and the mass comes up. That's why you design fins in the rockets, to lower the center of pressure and keep the center of mass up, to stabilize the rocket. Now, if you use both of these methods, the moving nozzle and the fins, you stabilize the rocket way more than you would by using just one of them. So that's pretty much it. We learned about the rocket, we learned about the aerodynamics, the fuel, the stability, the center of mass, center of pressure. I think that's much for today. Too much will cause indigestion. Okay, so thank you very much. Hope you like it and enjoy it, and please do subscribe, and if you have any problems, just comment below and I will be more than happy to answer your queries. And if you have any requests, special requests for special videos, just tell me and I will just do them without any problem. So thank you very much. If you want to reach me, you can reach me by WhatsApp, by Facebook, by Instagram. Oh well, Instagram is just for photos. You can reach me by WhatsApp and Facebook. You can subscribe to my channel, and I'll be more than happy to listen from you. Hope to see you in the next videos. Thank you. Goodbye.